So before we move on to looking at the wave functions themselves, I want to briefly have an aside about how these energies that we get from the solution to the quantum harmonic oscillator relate to vibrational spectroscopy. So in vibrational spectroscopy, this is using infrared light, and we can actually cause molecules to move between these different energy levels. Most commonly, we'll look at a case where we have a molecule that starts in V equals 0, just minding its own business. We hit it with light and it gets excited to V equals 1. And so then the question is, what energy does this correspond to? So whenever we're looking at spectroscopy, so this is light being absorbed, we could also do emission of light. You get sort of the same thing here. What we care about is the difference in energy. And this is going to be a theme. We saw this with the hydrogen atom. That's going to be a theme for all spectroscopy. We're always looking at differences in energy levels in our quantum systems. So we can take the difference in energy for V equals 1 minus energy for V equals 0. So that's 3/2 h nu minus 1/2 h nu. And so our energy difference is h nu, and it always will be. So these levels are evenly spaced for an actual exactly harmonic oscillator. For anharmonic cases, of course, it doesn't work out to be exactly this value. And so what we'll see is that this difference in energy, this is the energy of the light that will cause this promotion of our molecule from the lowest energy vibrational state to the next highest energy vibrational state. And so the transitions that we see are where we have changes of V of plus or minus 1. Now, this is what's known as a selection rule. And according to the symmetry of the system, these are the only possible transitions that we can see. Now, I would say this is more like guidelines than rules. Because we don't have an actual harmonic oscillator when we're looking at real molecules, we do see other transitions as well. And so we will see also, you can see delta V equals plus or minus 2, or even higher than that. And these are known as overtone transitions. These will be much weaker. The transitions will absorb less light than what we call the plus or minus 1. These are known as fundamental transitions. So these will be strong, and these will be weaker, but still observable. If things behaved exactly as a harmonic oscillator, we wouldn't see the plus or minus 2 or 3 or 4 or whatever else. And so if we want to write this in units, so this here is in units of hertz. If we want to write this in units of wave numbers, which is what I'm used to using as a spectroscopist, what we want to do is rewrite. So wave numbers, just as a reminder, is 1 over wavelength, and it's generally given in units of centimeters to the minus 1. So if we take our vibrational frequency, add this factor of c in here, but still have the square root of k over mu, we can rewrite this as our energy levels will be equal to nu tilde times v plus 1/2, where nu tilde represents our vibrational frequency, but we switch the units to wave numbers. And again, this is given by this equation over here. And so this is the way, and sometimes you'll see this same thing written as omega e. We'll actually use sources that use this notation as well. This is the exact same thing, so I'll just put an or here. And so this is just to write it in units that I'm used to. And so the difference in energy then becomes delta E is just equal to whatever that vibrational frequency is in wave numbers. And so this is the way I'm used to thinking about the units on this. But we have lots of different units, and you need to practice switching between all the different units. So in class, we'll talk about how so there's a relationship between the frequency we observe and K and mu, and we'll look at some examples of that in class.